Okay, let's study numerical differentiation for programmers. So actually, it's very direct for to implement numerical, well, to find different derivatives in numerically, especially for programmers. Okay, so I told you I just in last lecture slide I told you that there are two a little bit different ways to obtain derivatives of a function fx. Some analytical differentiation is more familiar to you if you have done it some numerical methods. But for programmers, it is very straightforward to implement numerical methods because you simply compute. You simply code a function to obtain the return value of the function you would like to compute, and then simply find the difference. Okay, let's just skip this part. And so let's assume that your current point of computation is x, and you'd like to compute the differentiation in x plus delta x, and in this case, delta x is a positive number, so you can obtain an approximated value of df dx by calculating fx plus delta x, this number here, minus fx here, over delta x. And this is called the fold differencing. And if we use negative number for numerical differentiation, then it's backward differentiation. Okay, I'll give you an example, right? So x is number 1.0 in this case, and dx is 0.1. dx is 0.1. So df here is f1 plus delta x minus fx, right? So df can be calculated in this way: get f x plus dx minus get f x. It's simple implementation. So df over dx can be computed df divided by dx. So the result will be 0.5 in this case. Okay. If we need to obtain this is we use the gradient or df dx, the derivative of x with respect to x, to make an expectation of the value here. Okay, so let's go back to this slide. We calculated the derivative of x over x with delta x equal to number 0.1 here. So we obtained derivative here by using this value. Now we can use the same gradient, the derivative, to make an expectation at 1 plus 0.2 instead of 0.1. Right? Okay, so let's do simple math. So let's assume that we know the derivative here. We know this number. Then we can make an expectation of function, the value of function f at x plus delta x by adding this term to current fx. Okay, so I'll give you a numerical example here. So we want to make a guess of the value of function f at 1.0.2. We don't know this value, but instead we know df over dx at this point. In this case, we can make an expectation here. So following the equation in previous slide here, fx, f1 was 0.6 here, and df dx1 at x1 was 0.5, and in this case delta x, the difference between this x and this x is 0.2. So f1 is 0.6 here, and df over dx is 0.5. It was 0.5 by calculating here. In this case, we use delta x 0.1. And in this case, we want to know the value of fx here. Here, the delta x target is 0.2, not 0.1 here. So the result is 0.6. It's an expectation, and this process is Euler integration. And here is an example code of the same process. So in some cases, in previous case, we wanted to make an expectation of the return value of function f at different the calculation point x rather than the central x. I mean x plus delta x target. We wanted to know the value of this part. In this case, we can consider one more different case. So we want to find delta x target instead of the value of function f. We want to find delta x target which satisfies a condition f is equal to f target. In this case, f target number is given, and we want to know delta x target. They are different. So in this case, by moving this one to this part and this one here, then we obtain delta x target is equal to, can be approximated by, because this is a numerical method, so it's an approximation. So f target minus f over df dxx. So we know this one, and this is given, and we want to find this one. So we can do a simple math one more time. Let's consider that f target is 0.7. This is given number, and we know that f1 is 0.6, and we also know that df dx at x is equal to 1 is 0.5. So 0.7 minus 0.6 over 0.5 is 0.2. So we know that, if the input number, the x, the proper x to obtain f is equal to 0.7 is 0.2. So 1.2. Here. And here is the code. Okay, and in previous example, we did it with numerical differentiation. But well, in some cases, well, if the function is simple, then we can use analytical differentiation to find the proper delta x target, or find the expectation of the return value of x. Okay. So you can simply replace. Let's go back to this. Yeah. So we use numerical differentiation for this example here, but we know that, well, the difference, the finding the gradient of a line is very simple, because it's just a constant. It's constant. So we can use it instead of numerical differentiation. Well, so it depends on the cases. Okay, so I'll keep talking about gradient descent method and chain rule.